Okay, so welcome everybody. We are now proceeding to the defense of the master thesis of Mustafa Busaka El Bojani, and the title is Age of Infection Disease Modeling from Kermack and McKendrick to Multi-Compartment Models. Mustafa.
Okay, great. So I don't need to present this slide here, so we already gave the title, so that's great. So let's go on. So in this presentation, we will initially focus on the work by Kermack and McKendrick that was presented almost 100 years ago in 1927, and it's titled A Contribution to the Mathematical Theory of Epidemics. And this model is very important because it's the first model that first integrates the concept of age of infection, which is the time since the infected individual was infected. The work is often misunderstood or simplified to the SEER model. So most people understand the Kermack and McKendrick model simply as the SEER model, but we'll show that Kermack and McKendrick equations are much more general than the SEER model, because the main limitation of the SEER model is that it doesn't account for an infection rate that depends on the age of infection. It uses constant infection rates and recovery rates, as you may. Then we will introduce the multi-compartment formalism in order to deal with an infection rate that depends on the infection age. And this will be particularly necessary when the Kermack and McKendrick equations become impractical and difficult to deal with. And why do we want to consider an infection rate that depends on the infection age? That's because most diseases like influenza, COVID-19, sexually transmitted diseases have a viral load, like an infection viral load or infectiousness curve that depends on the age of infection. And this is very important to be modeled in these diseases. And here we have a small sample of their old paper, almost 100 years ago. So the main assumptions of the Kermack and McKendrick model is that the disease leads to either complete immunity or death. That means that a recovered individual cannot be infected again. Then all individuals have the same probability, all susceptible individuals have the same probability of encountering an infected individual, of being infected by infected individual. And we will also always use the assumption that the population is closed and sufficiently large. So, and these are the equations that Kermack and McKendrick present. They're somehow a mixture between differential and integral equations. They are called integral differential equations. S is the number of susceptible, R is the number recovered, and for the equation of I, they don't give the derivative of I, but they directly give us this expression here. And tau is the age of infection, which is the time elapsed since infection took place. And all these integrals, all these three equations are related through these important variables, through these important functions A, B, and C. In this case, phi of tau is the infectivity rate, which is the infection rate, the number of infections we have per unit of time. Psi of tau is the recovery rate, is the number of recovered individuals we have per unit of time. And B of time is the infection period distribution that follows exactly these ansatz. The infection period distribution is the probability that an infected individual at time tau is still infected. So let me explain it in other words. If you wonder yourselves, what is the probability that an infected individual is still infected at tau equal to 10 days, for example, this probability of still being infected is given by this function here, which we call the infection period distribution, probability distribution. And we will also use a lot throughout this presentation the reproduction number, which basically measures the number of secondary infections produced by one infected individual when introduced in a susceptible population. And somehow this reproduction number measures the impact the disease and predicts the outbreak of the disease. If the reproduction number is smaller than 1, you won't have any disease outbreak. And if the reproduction number is bigger than 1, we will have a disease outbreak. So we have an infection peak and so on. And the expression for the reproduction number for the Kermack and McKendrick equations is given by this expression that we proved in the thesis. It's basically the integral of the function A, which is sometimes called the mean effectivity. And the Kermack and McKendrick equations will deal basically with two models. The SEER model that uses a constant infection rate beta and a constant recovery rate gamma, and this constant recovery rate gamma has as a consequence an exponential age of infection distribution. If you apply these equations like these conditions to the equations that we found before, we deduce the famous Sear equation, Sear model equations, and this is the reproduction number of this model. The second case we will deal with in this Kermack and McKendrick formalism is this Gaussian model, in which we still consider a constant infection rate, but now the infection period distribution will be a Gaussian instead of an exponential, and this gives rise as a consequence the recovery rate won't be constant anymore, but will depend on tau, linearly on tau. So this is telling you that the recovery rate is proportional to infection time. So the individuals that have been infected for longer are recover faster, or are expected to recover sooner from the disease. If you apply these equations, these conditions to the equations that we saw before, we get these equations. In this case, we cannot obtain ordinary differential equations as before, and this can be easily solved numerically. And this is the reproduction number that we deduce for this Gaussian. Then we will jump to this multi-compartment formalism in order to deal with an infection rate that depends on tau, because this is something that we haven't done in the Kermack and McKendrick equations, because they become very difficult to analyze, as you may have seen from the thesis. And in this case, this multi-compartment model that we call SINR is simply an extension of the Sear model. So instead of having just one infected compartment, we have n infected compartments, one for each infection rate beta and infection time tau. And the infectiousness or the infection rate will follow this function here, basically a gamma distribution, and this function is very suitable because it mirrors the typical viral load or infectiousness in most infectious diseases. So at the beginning, we don't have the individual is not very infectious until we reach a maximum. Then the infectiousness decays with tau. So the total infection time will be tau sub r. This is the recovery tau, which will be the number of compartments time delta by tau, because delta of tau is simply the time that each infected spends at each infected compartment. And these are the equations that represent like this multi-compartment model. So if you use the case n equal to 1, you will get you can get yourselves convinced they will get the Sear equations, the Sear model equations. And we will use capital N, do not confuse this n with the small n, capital N as the total population equal to 1. So that's usually done with the iterator. The interesting thing about this model is that we can get a reproduction number through the next generation matrix. We don't have to explain that here, but this is how this method works. We don't have to explain this, but this is the reproduction number for this multi-compartment model. And the continuous limit, get to the continuous limit when we take n go into infinity. And as we can see, the equations can be easily generalized to the continuous limit when we take this limit. And we get some sort of transport equations. Do you see like this third equation converts to this transport or continuity equation? And the second equation turns out to be the second, and the fourth turn out to be boundary conditions. That is the final, this is like the entry condition, the entry boundary for the infected, and this is the exit boundary for the infected individuals. So we have 0 infected individuals at the final time so far. So these are the boundaries. This is the equation that's telling us the transport of this model. So I want you to understand that when we take the continuous limit, this model can be the infection process can be understood as a transport or flow of all the infected individuals through all stages of the disease, through all the infected compartments. So then we will apply this multi-compartment model to a vector-borne model. So in this case, we have a host population and a vector population. In the host population, we divide again the infected compartment into n compartments. And the important thing here is that the hosts get infected from infected vectors, for example, through a bite. And the vectors, the infected vectors, get the infection from infected hosts. So hosts become infected from infected vectors and vice versa. Vectors become infected from infected hosts. And as you can see here, we do not consider host-to-host infections, host-to-host interactions. So hosts, in this case, only get infected from vectors, not from other hosts. So there's no contact between hosts, because this model is applicable. For example, this model that we show here is applicable to when the hosts are plants, for example, trees, and are affected by this pathogen, Shigella fastidiosa, that's quite known in the Balearic Islands, and it's transmitted by this vector, by this insect. The vectors are those insects that transmit the disease, by the way. And again, we'll have the total infection time will be tau sub r, will be the number of compartments times delta tau, which is the time that each infected host spends at its infected compartment. So in the vector population, we consider birth and death rates. That's something that we do not consider in the host, and we will use equal birth date rates delta and death rates mu in the vector population in order to have a stationary population in order to have a stationary vector population. And the hosts will experience an infectiousness, like an infection curve, infection rate that follows this function again, this gamma distribution that we showed in here. So for the calculation of the reproduction number, we will need to use the next generation matrix. And for that, we need a stationary vector population. If you need to know why, you can ask me more details later. But this is the number of infected vectors, the dependence of the number of vectors, the population, vector population, the dependence of the vector population with time. And in order to have a stationary value for the vector population, we need to take the limit t going to infinity, or we can use equal birth and death rates. That's what we do in the medical study. We take equal birth and death rates, this vanishes, and we get simply that the stationary value of the vector population is simply the initial value number of infected hosts, the initial value of vectors. And these are the equations that deal, these are the equations that represent the model that we showed in this schema here. And the reproduction number that we get from this model is given by this expression here. And this expression for the reproduction number proves the effectiveness of control measures. So we know that if we want to control the disease, we need to control the vector population, which is obvious, but it is proved in this equation. So we need to have low birth rates, high death rates, and low vector population at the beginning. And in order to decrease, another way to decrease the reproduction number is by acting through these alphas, not through these infection rates. I know that there are no vaccines for trees and plants, but in the case of hosts, this sum here can be reduced by the administration of vaccine them, medicine them, and so on. These are the equations. I will explain them. So as you can see, the hosts, we have a loss of hosts due to an interaction with an infected vector. So hosts get infected from infected vectors. And in this case, we have a loss of susceptible vectors through an interaction with all infected hosts coming from all the compartments. So vectors get infected from infected hosts. And these equations can be easily generalized to a case in which we have host-to-host interaction. For example, host-to-host interaction. For example, if you want to model a vector-borne disease like malaria, in which there is also contact between hosts, between humans, these equations are very easy to generalize to this case, but we won't use this in the medical study section. So this is the Kermack and McKendrick results. In the first two figures, we show first two figures represent the SIR model, in which we have a constant infection rate and constant recovery rate, and in infectious period distribution is an exponential, and this is the reproduction number that we saw before. And here we are analyzing the Gaussian model, in which we have a constant infection rate, but a recovery rate that depends on tau that gives rise to this Gaussian infection period distribution. And this is the value, the reproduction number that we used before. So what do we see in here? We see that if we increase gamma, we have a lower peak at the end. We have a lower infection peak. That's because if you increase gamma, you have a smaller reproduction number. And here, what we observe is that if you lower the value of sigma, which is the width of this probability distribution, if you lower sigma, you get smaller infection peak times as well because of this. Because we are lower at the end of the day, we are lowering the reproduction number if we reduce the number of sigma. In this case, we analyze for the Gaussian case the final size of the disease in terms of sigma and the reproduction number. The final size is equal to the final number of recovered individuals. So here, for each beta, for each infection rate, we see a different threshold for sigma. And this threshold turns out to be unique when the x-axis is reformulated to the reproduction number. So in this case, for all betas, all the curves like collapse, and we have this figuring here. What is this telling us? So this is telling us that for reproduction numbers smaller than 1, this is the expression that we're using, that for reproduction numbers smaller than 1, we don't have any deaths at the end of the pandemics. And starting from 1, which is the threshold value, we start having deaths at the end of the disease. We have the disease already. So this proof that this formula here is correct, is solid, is consistent. So now we jump to the multi-compartment model, which is, as I said before, an extension of the CIR model, just by dividing the infected compartment into n compartments. Here we observe that the final number of recovered and susceptible individuals is the same, independently of the number of compartments that you consider in the infected population. And the number of infected at the end of the disease will be always 0, of course, in any case. And what do we observe here? We observe a significant difference in the dynamics. So as we increase n, you can see in this right figure, as we increase n, we have higher peak times and higher peak magnitudes. So the peaks are higher, and the peak times are smaller as well. So we have higher peak times that happen before in the timeline as we increase the number of compartments. And here we do something similar. Here we are analyzing the infectious peak amplitude and the infectious peak time with respect to n while keeping the reproduction number constant. So here, for the same reproduction number, we observe that increasing n increases the peak amplitude. And here, increasing n makes the peaks happen before in time. So increasing n decreases the value of this infectious peak time. And what do we observe here? We observe that we get to constant values regardless of how much you increase the number of compartments. So for example, starting more or less from n equal to 200, we don't observe any change in the peak amplitude or in the peak time. So remember that when we increase the number of compartments at the end of the day, we are discretizing this infectiousness curve. And we don't need, this is telling us that we don't need to over discretize or use a lot of compartments in order to consider a continuous case or continuous infection curve. So it's enough to take these small values of the relatively small values of the number of compartments from the numerical point. And here we are analyzing the multi-compartment model applied to the vector-borne model. So in these cases, we are comparing n in the single compartment case, n equal to 1 with n equal to 100 for the same reproduction number, for reproduction number equal to 2, and here for reproduction number equal to 3. What do we observe? As we increase the number of compartments in the host population, we get the same final state, same final steady state usually, but very different intermediate dynamics. So as we increase n, we observe again higher peak times, higher peak magnitudes, and the peak times are smaller, so they happen before the timeline. And here observe the same for reproduction number equal to 3. If you increase n, you will have higher peak times, higher peak amplitudes and smaller peak times. Here we display as well the dynamics of the vector population. Observe how in the vector population, the I and S curves are symmetrical. That's because we are considering a stationary vector population that's equal, that means equal birth and death rates. Here we visually see more easily the difference in the dynamics as we increase n. So for the continuous, we are comparing again a single compartment case with a continuous case, and we observe in the continuous case much higher peak times, much higher peak amplitudes and smaller peak times. And we observe something additional. We observe a significant difference in the time that we need to reach the steady state. So the disease duration here, the disease lasts significantly shorter than in here. No, here in the single compartment case, it takes much longer to reach the steady state. This is another thing that we observe. This comparison was done for the same reproduction number, by the way. And here we have a heat map of the number of infected hosts with respect to time in the horizontal axis and the infection time tau in the horizontal vector, in the horizontal axis. And here we visualize this transport or wave nature that we observe in the continuous case. No, so here as we increase the number of compartments from n equal to 10 to n equal to 100, we observe that this beam turns out to be more yellowish and slightly shifted to the left. That's because we have higher infection peak time, higher infection peak magnitudes as we increase, and smaller peak times. So as you can see, we can visually see like the transport of these infected hosts through all infected compartments. When we go to the continuous limit as we increase the number of compartments. So here we are analyzing 4 magnitudes in this vector-borne model. 4 magnitudes. We make a comparison between the single and the multi-compartment cases, n equal to 1 and equal to 200, which is the continuous case, and we do the comparison for the same reproduction number. This is very important. The magnitudes that we compare is infectious peak time. So here we observe again for different values of the reproduction number, we found higher peak times for the continuous case. Regarding the infectious peak time, we find that in the continuous case we have smaller peak times as we saw before. Here we're comparing the disease duration. So here we see that in the continuous case, the disease lasts significantly shorter than in the single compartment case, and the only magnitude in which we don't see any significant difference is the final size of the epidemic, the final number of recovered individuals. As you can see, they are almost the same, regardless of the number of compartments. You see a small difference here, but this is very small numerically. The maximum relative difference that we found is 2%. So the very important conclusion that we get from these figures is that regardless of the number of compartments, we get to the same final state, but with very different intermediate dynamics. And why are we comparing the single compartment and multi-compartment cases? We're doing this in order to show the necessity of using multi-compartment cases. So if for the same reproduction number, we could get exactly the same dynamics for n equal to 1 and n equal to 200, then our formalism will be pointless. But in this case, we see very different dynamics in the middle, despite having the same final state or the same final number of recovered individuals and susceptible individuals. So this would be an important conclusion as well. There's another thing that I want to mention. Here we've seen that we have significantly longer peak amplitudes in both in the continuous case, but we have the same number of dead individuals. So one may wonder, why do we have the same number of dead hosts if we have a much higher infection peak time in the continuous case? So the only way we can justify A and D like these two figures is through the disease duration. So we have the same number of recovered individuals at the end, because the disease duration lasts longer. The case in which we have a smaller peak time. So that's maybe a question that you may have wondered yourself. Why do we have the same number of recovered individuals if we have a very huge difference in the infection peak? Because a higher infection peak should lead to more deaths, but in this case, the disease lasts longer for the case in which we have a smaller infection peak, which is the single compartment. So finally, as conclusions, we introduced the epidemiological model that is introduced the concept of age of infection. This is Kermack and McKendrick model. Then we deduced the SEER model as a consequence of this more general model, and a Gaussian of the Kermack and McKendrick equations. From this Gaussian model, we couldn't find ordinary differential equations, but we could numerically solve the equations, and we found an expression for the reproduction number that correctly predicts the outbreak of the disease. Then we applied this multi-compartment formalism in order to address an infection rate that depends on the infection time, because this is something that cannot be done easily. The Kermack and McKendrick equations. This multi-compartment formalism turns out to be more practical than Kermack and McKendrick equations. And we finally applied this multi-compartment model to vector-borne disease, and we compared the single and multi-compartment cases, the single case and single compartment case, and the continuous case. And we found that the final state is practically the same. The final number of recovered hosts, or dead hosts, is practically the same. But the intermediate dynamics are very different. You get much higher infection peak times, and much higher infection peaks, and shorter peak times for the continuous case. And this is very important from the epidemiological point of view. For example, that having a high infection peak can lead like to health emergency or to a collapse of the health system, and this cannot be predicted by the CIR model, but single compartment models. These simple multi-compartment models can predict like these scenarios. No? And that's all. Thank you for your attention.
Thank you.
The sound is not very good, Pera. I think I can hear you better from the wall. So I will stop the recording. Take care of the sound.
Yeah, I cannot hear you either.
Yeah.